Thank you for the introduction. Hello, everyone. My name is Lee, and I'm from ViDAR Lab at Shanghai Lab. And my talk today will be visual models and foundation models for autonomous systems. Okay, let's start. Okay, so we are living in a very complex world. Like we have very complex teaching indoor houses, and we have very complex factory scenarios, and we have complex outdoor environments. Like the picture I took today outside of this simulation center. So we have. Okay. And we live in the world, but nowadays we are building the robots and autonomous vehicles, and we call these systems as autonomous systems. And we would like them to behave like humans, to act as an artificial general intelligence. Like we have humanoid robot, we have robot arms and robot dogs and robot vehicles. So these autonomous systems, they receive multimodal context, including sensing information or very high-level commands from humans or drivers or whatever, and they reason the world and they make actions and they interact with the world. So in a more formal way, everyone like this figure. So the environment gives the current state to the agent, and the agent do the action, and the environment then return the next state and the reward. This is a very traditional figure in reinforcement learning and policy learning. And in reinforcement learning, people find that exploration space is too high, and they want to make a world model to represent the environment, to select some very complex concepts and model the relationships between the agents and the environment, and to represent the whole system. So the world model typically has a memory component that makes predictions about the future based on historical information, and humans can train another simple and very shallow controller or policy network with an internal world model. This is a very initial definition of world model we are talking about today. So as Yang said, this is a path towards autonomous machine intelligent version, and today we are talking about the world model and foundation model. So this is a history, and we get very traditional works like Dreamer series and some presidential papers. And especially in recent years, like in last year and today, we can see very popular and fascinating works like general world models from Tesla in last year's CVPR workshop, and Gaia 1 from Wave, and GenAD and Unify and Unison. This model also build a world of autonomous driving systems and some robot systems from large-scale videos. And today, we are questioning about what are the foundation models for our robots and autonomous vehicles. Actually, some may claim that like video predictions like Sora, they last year released this year, and some large language models. Some may ask if this video prediction model and large language models can behave like a world model for autonomous systems. The answer to us or to me is no, because they have very bad hallucination problems, and some you can see from these two figures in the left part, and you can see some research papers in ACL or some NLP groups. They claim that these large language models can behave very badly about some basic rules or some real-world common senses. So the question is what we should do to build a world model for these autonomous systems, or what is the foundation model for these systems. So as some speakers mentioned today, so the foundation model has to be trained on large power data, and they should behave very generalizable ability, and they can be fine-tuned or prompted to diverse range of downstream usage, and they generally has some self-supervision training strategies. However, there are some takeaways about this autonomous system, like they have label data for one specific task, such as image classification or image sanitation, and they are optimized text wisely, and they are supervised learning. But for our visual world model and for the foundation models, we need to train our model with raw data, and we need to incorporate the model with world knowledge. So we need to train our models with self-supervised manner. Unlike presenters speak lately today, they show a lot about vision language models or vision language action models. I personally will focus more on the repetition learning of the foundation models. So I will give talks about these three parts about data and model and applications. So really, I will talk about how we can find large corpus of data, especially for autonomous driving, to help our effective generalization. And how can we design a very effective world model with intricate world knowledge with self-supervised learning. And in the end, I will try to answer what the abilities of the world model in autonomous driving. So this is work of from a group and some collaborators from like Compound University of Science and Technology and Tübingen University of Tübingen. And this is the highlighted work will be presented in Thursday, and you can talk to us then. So a very quick overview. This is a very large video prediction model on web scale driving videos, as mentioned by NJ, and it enables the very great generalization across a wide spectrum of domains and tasks. So this is a dataset, and we have a model, and in the end, we have multiple tasks for downstream demonstration. First, data. So as you can see, we have many datasets in last years. So we have Kitty, Arborverse, Waymo, and nuisance, etc. So they are very relatively small scale, including 5 hours videos or sensor data in nuisance and about tens of hours data in Waymo or Arborverse. These are very small scale for training a very generalizable world models, since they are collected in a specific region, like nuisance is collected in 3 cities, and Waymo is most of the same scenarios in Waymo is in the Bay Area. So what we want to do is to find a large corpus data to train our very generalizable model. How to scale up our data. So this is a very good attempt. There are some good attempts in the industry, like in Tesla and Wave. But what we want to do in our academia is to find a very large-scale public dataset and build our own world model to show the ability of the world model to do some frontier research. So in our group, we developed the largest public driving datasets. We call it OpenDV, which stands for Open Driving Videos, and it contains over 700 cities and regions and over 2,000 hours compared to other public datasets. So basically, we collect data from YouTube, such as similar to the large language models. They collect data from the website, and we feature these datasets with very diverse geography, weather things, and we do not have labels for these datasets, so we have to find a self-supervised learning way to learn the world model. So some status it has over 2,000 hours, because we also include some public datasets in our own datasets, and it covers more than 700 areas, and you can find the datasets in our GitHub. It is shown as a YouTube link, and you can download them in your own drive, about tens of terabytes. So to download this data, we first manually screen all YouTubers with very high quality driving videos, and we select those videos and we annotate. We discard those low quality data, such as distorted frames and black frames. These are also some driving through instruction at the beginning of the videos and some separation note at the end of the videos. At the end, we want to add some annotations, especially the linguistic descriptions about the videos. So we manually fine-tune a multimodal model. Believe2 is very Believe2 to we fine-tune the Believe2 to the driving scenarios, and we pair the YouTube data with the fine-tuned multimodal model, and we can get a paired textual annotation and and the videos. The textual annotation includes a high-level command such as go straight or turn left, turn right, and some context to describe the scenarios. And okay, so after we can get the data, it has the large scale data in the driving scenarios, and we can train a very generalizable video prediction model. So the video prediction model is based on image generation model as stable diffusion XL, and we transfer it into a high capacity video prediction model. So this is the first stage. We train the image diffusion model based on our OpenDV YouTube data, and we can condition it on some linguistic descriptions and commands, and we can then transfer it into a video diffusion model by adding some temporal denoising layers and some temporal reasoning blocks. And specifically, we can add some core designs to make it generate very high fidelity videos. So first, we integrate some temporal blocks to between the spatial attention layers to make very sufficient spatial temporal interactions, and then we also in the attention layers we design some decoupled spatial attention to efficiently model the long-range modeling about the x-axis and the y-axis in the image. And then in the temporal layers, we add some causality masks to predict very coherent predictions, and also more importantly, we need the causality masks to avoid some causal confusions in the temporal dimension. So I just gave some basic methods. You can refer to our paper, and we just quickly go into our results. This is a very concise comparisons about some image or video diffusion models, 2 hours. We can get very decent zero-shot video predictions on bouncing datasets. And other text or downstream applications include language condition prediction, such as we can condition the model with different high-level fonts or very specific descriptions, such as a parking lot or some high-level commands like turning into the mountain, and it can generate some counterfactual results. So we can instruct the future with free-form text. And besides text, we can also fine-tune our model to action conditioning. So it behaves like the simulation in this task. So basically, we fine-tune our model on new things, and we can inject the model with the trajectories, and it can predict videos based on the conditioned trajectories. So basically, it simulates the future differently conditioned on the given trajectories, but there are some other conditions, and we like angles or velocities and some action command. These are not incorporated in this work, and we will introduce shortly. And the last question is about how can we apply this for representation learning. And in this work, we freeze GenAD model, which was a video diffusion model in our work, and we freeze it and add a very shallow, lightweight planner above it, and we can predict the motion planning results. And surprisingly, it achieves very similar performance compared to GenAD, which it only has very limited training parameters, and we can achieve this very quick training time without the ego status. So From this work, we can have some takeaways, some specific takeaways, like we now introduce a very large-scale available driving dataset. It has 2,000 hours of videos, and the great diversity ensures the generalization. And for the model, we have a video prediction model conditioned on high-level instruction. And sorry, I'll just. And for the application, we can learn the learned application can be simply trained for policy prediction and some language condition or some action condition applications. As I mentioned, so in this work, we only condition the model with action trajectories, but how about some other conditions we can directly apply in the real world, such as velocity or angles and some high-level commands. And additionally, how about the typical applications such as the rewards for model-based reinforcement learning in the traditional pipelines? So this comes the following up work about we introduced about Vista. This is work on archive, and you can also refer to the paper about some details, and I will just briefly introduce it. So compared to existing driving world models, you can see this is data from OpenDV YouTube, and it has very large, huge resolution. But the most important thing is here we want to inject the world model with multiple action control modes. Like here we can have angle and speed and the trajectory and font and goal point. These are all very common conditions in the real world, and we need them to show as a very unified representation to the world model. So this is a typical video depiction model, like we have initial brain as conditions or primary brain as conditions, and we predict the future prediction. And here, this is a special point about Vista is we condition the model with multiple control conditions, like high-level commands and high-level goal point, and we have also low-level conditions such as trajectories, angles, and speed. These multiple conditions can behave very unifiedly to condition the video depiction model. And here are some techniques we use to make this in real. So to generate a very high fidelity videos, we need to inject some dynamic priors, like we can replace the latent to absorb varying numbers of condition frames, and we use two novel losses to inject some dynamics of weight and preserve high frequency structure features to make this make the videos very high fidelity. And this stage is trained solely on YouTube data. And for the second stage, we train the YouTube data and the nuisance data, which contains the the whole suite of action conditions, and we can call-train them into a action condition video prediction model. So this is efficiently trained via LoRa strategy, and in fact, this can be trained in several hundred hours, but the second stage we only need tens of hours. And after the second stage training, we can realize versatile contributive condition on the unified action conditions. Okay, here are some results, and I didn't put some existing works results here, but I only put our results. So our model can show very high fidelity future predictions, like the resolution is very high, and we can also regressively condition on the generated frame to roll out very long horizon videos. And the most important part is our zero-shot action contributing. So our actions are only available on nuisance, but due to the co-training strategy, we can zero-shot our action on YouTube data. So this is from the YouTube data, but we can also give some high-level commands or very specific trajectories or angles and speed, and it can predict corresponding videos based on these actions. So for now, this is world model part, and we now want to see how it can apply into the traditional reward pipeline. From the previous works like Drive W and Drive into the Future, they get the reward from a detection model. So, like they predict the future and they use detection models such as object detection and map detection to perceive the world, and they calculate the collision rate or some distance to the boundaries to get the final rewards. However, this includes an additional steps, so we are wondering if we can provide the reward without branch-choose actions or additional detection models. So we resort to the uncertainty method. Here, I show the results of reward about, corresponding to the average L2 error. Though L2 error is not ideal in open loop settings, but for a conceptual way, you can see that lower L2 error corresponds to a higher reward. So it means that the reward indeed captures the conceptions about how to drive very well or reasonable in the complex driving things. So in this example, so you can see that when we drive along the road, you can get a relative higher reward. And in this example, though the red points correspond to some lower L2 errors, because the recorded trajectory is much more smaller or shorter than the green points. But in reward part, we can show that the reward for the green trajectories are much higher. So this shows the reward from our model is more reasonable than the average distance error. So this is a summary about our Vista program. So we can inject all kinds of conditions with very efficiently to make it a real world model compared to the GenAD project. And for the application of our stochastic diffusion process, we can learn some uncertainty and transfer it into a very inherent reward to help some model-based RL functions. But the reality is that we cannot apply these models in the real world, because applying this diffusion model on vehicles is very time-consuming, and we do not have such large-scale data, like hundreds or millions of data in the industry to realize deployment. And so the next question is, can we have more industry-friendly approaches like data model and text applications? Also, how can we evaluate these models, as Ted just mentioned? There comes another work in our group, so we resort to the LiDAR points. So LiDAR is viable sensors in the industry for many years, and the people have developed some future prediction models based on LiDAR points. And in last year's CVPR, CMU has also invented some methods about world model to turning the LiDAR prediction into a faulty occupancy prediction. And so in our group, we are thinking about the images captures more semantic clues, but LiDAR have some geometric clues. So can we combine them to generate a multimodal world model to get a very strong conceptual in both semantics and geometrics? So this is our work about ViDAR. So ViDAR is actually has some previous names in both CES and TRI. They are mostly about multi-view stereos or self-supervised designation. So these works are mainly for reconstruction purposes, but they lack of exploration in temporal dimension. And since the reconstruction purpose mostly focus on the geometric expectation, so they lack the reasoning ability of the environment. But we think if we can condition these models, condition the models on the ego motion or ego planning status, we can turn these models into a world model and also get the reasonability of the environment. So This is also a highlight work in the CPR and on Thursday, just beside the GenAD project, and you can also go there to have further discussions. So I will introduce this very briefly. So for this work, we train a multimodal world model by visual point forecasting, and it actually can boost the end-to-end world driving. So the concept is that we input history visual inputs, and our ViDAR model, visual point cloud forecasting model, we predicts future point clouds, and we can use the pre-trained visual encoders to various downstream tasks. Like we can apply it into detection tasks, and we can use it for prediction models because we are building some temporal reasoning abilities for the model. And in the end, we can also use it for planning. So the method is very easy, and we have history encoder, but to help the rendering part in the image domain, we need a latent render to solve the ray shape drawbacks in the image in the BEV features. And finally, we have an auto-regressive future decoders to decode the bird's eye view features and decode into occupancy and LiDAR points in the future. So these are the results, and as you can see, we inject action conditions in here as future ego motions, and so we can condition these ego motions as a decoder input. And in this example, we can condition this as go straight or turn left, and future LiDAR prediction can behave similarly as LiDAR commands. Okay, so it can also effectively model relative motion because we explicitly build the correspondence between LiDAR points and these objects. And finally, we can apply it into end-to-end driving, and with the pre-trained ViDAR encoders, the GenAD model gets much higher performance in all these tasks in the driving stack. So for this part, we have another summary here. So the image LiDAR pairs are very helpful and to capture both semantic and geometric information in the environment. And for the model part, besides the video prediction models, we can also build some bird's eye view based models to effectively model the world. And for the application, the spatial temporary layer, the spatial temporary pre-training techniques improve all tasks in driving and serves as a foundation model. Okay, so how about robotics? So one model in driving is relatively very straightforward, and we can predict future based on the images and the LiDAR points. But how about the robotics? Like Unison, they model the world with very large corpus of data, but the challenges in robotics is that we have very heavy interactions between the robots and the environments, and how we need to build the interactions. And another point is there are more diverse tasks and environments in robotics, such as indoor manipulation tasks or some navigation tasks, but the vehicles are only running on the roads. So we are still recording these points, such as we are using visual data, and we need to encode the world knowledge, and we are resorting to the representation learning techniques to improve the robotics tasks. So, but the additional point is about the visual world models compared to the driving is that we need to highlight the interactions in robotic applications. So here is the work about learning manipulation by predicting interactions. So there are some representation learning frameworks in previous works like conjunction learning or MAE-based methods or video prediction methods. They mainly focus on either high-level semantics or very low-level details. But as I mentioned, we need to highlight the manipulation tasks about the interaction process. So here in this work, we explicitly model the interactive dynamics about the patterns of behavior and the physical interactions. And we can get both the high-level semantics and the low-level details. So this is work about published in Robotics Science and Systems and will be presented next month in Delft. So to realize the objective about manipulation interaction and about the world model, so we have two parts for the modeling part. So one is where to interact corresponding to the objects and how to interact corresponds to the world model. Like here, in this part, we build how to interact based on two sets of frames. Like for one, we can predict the transition frame with the initial frame and the final frame. And another part is we can also predict the final frame based on the initial frame and the transition frames. These two conditions also help our generalization about the world model. And where to interact corresponds to we need to detect the objects we are interacting. This transition and the future states can make our visual models highlighted with interactions. Okay. And for the robotics application, we do not have very large-scale robotic datasets, so we can only use some public human interaction datasets such as Eagle4D, and we can build our model, build our reputation learning model with VIT encoders and distributed language encoders, and we pre-train them to predict to our two objectives. Sorry. So this part corresponds to the image prediction, and this part is a detection test. So they are for two objectives about where to interact and how to interact. With the pre-trained encoders, we can do some real-world experiments to add a very shallow MLP policy head to predict to learn the policy, and we can also do some complex tasks such as in the manipulation. And we can also refer some objects and ground them in the image. As you can see, we achieve very good performance compared to some existing works. So here are some generalization results about the very object and the backgrounds. So final part, how about video prediction in robotics? The MPI work also still predicts only one frame, but how can we apply the popular video prediction work in the robotics? So the challenge here is video prediction is hard to determine the transition and the replay. Like in this task, we can only we have very relatively long horizon tasks, and we need to use some large language models or whatever models to divide these tasks into some subtasks. But how can we determine if our video prediction is finished, or when we should replan the video panel? So in this work, this is a work on the review. So but you can see it on archiving reason in the future lately. So in this work, we learn from the closed loop controlling the traditional pipelines, and we find that based on our error measurement learning and our latent can get very high quality and high quality latents corresponding to these circles, and we can use these very good patterns to determine our replan and the transition stages. So these are our findings from the video prediction for robotics, and here's the final conclusion. So for world models in autonomous systems, we can have utilize the visual data to utilize the large-scale videos such and the image that appears to get a very generalized world model by self-supervised learning. And models can be very diverse, including the diffusion models and the bird's eye view prediction models, and we can utilize multiple conditions, and they can also as very effective environmental objections. So diffusion models can be some research-based, but bird's eye view may be some very friendly formats for the industry. And for the application, the world models can learn some very good representations, and they can help downstream applications, including policy learning and reward evaluation and diverse driving tests. So this is a conclusion: visual models as foundation models for autonomous agents, and my prediction for the future is we can incorporate more large language models or VLMs to the visual models, and they can get much more stronger abilities, including the language abilities. So they can, in the future, they may behave as the foundation models for autonomous agents. Thanks. That's all for my today's talk. I'm happy to answer some questions.
Yeah, please. Just one clarification question. Where do you get your data from? Your videos?
Which work?
The first one.
Okay, so yeah.
You get it from YouTube, you said?
Yeah, actually, the full data set has. Wait a second. Sorry. Yeah, so the full data set has multiple parts, so it also includes some public data set, but the main part, like YouTube part, has 1,700 hours of data. So the main part is from YouTube, but it has no labels, and we can get some additional parts from existing data sets.
So that's driving data.
Yeah, these are all about driving data sets, and this is the largest data set we can get. We believe.
And I was wondering, actually, my question is, like, you don't want to. I mean, I guess you want to have diversity of data. Otherwise, if I give you 1,000 hours of highway driving, it's not very useful.
Yeah.
How do you calibrate that?
Indeed, we didn't calibrate, or we didn't choose which data we to reserve. We only reserve data based on their quality. But in fact, there are many highway data on the YouTube, and but in this public data, they also have some very urban complex scenarios, and we believe this actually behave very similarly in the real world. Like people in most times people drive from the highways, especially in the Western countries. But like in China or some developing countries, people can drive most times they drive in the urban cities. So this is a very natural distribution, and we don't do much balance or about that.
I have about the visual LiDAR.
Uh-huh.
I would like to learn how to train the.
Okay. So this is the question. The question was how we train this visual LiDAR, right? So it is self-supervised because we have image and LiDAR pairs, and we input the historical images, and we predict future LiDARs based on the conditions. So this condition is unique during training, and we can supervise the model with collected LiDAR data. Yeah. This work was trained in image and LiDAR peer data set. Okay. So the question was how can we balance scarcity about the dense LiDAR points? So the way is that we first predict the bird's eye view features as shown here. We predict future bird's eye view features, and we convert it into 40 occupancy in this work. I didn't show here. So we first created for the occupancy, which was 3D occupancy in the temporal dimension, and we can render the LiDAR points based on the mechanism we think that the LiDAR points should cast.
Yeah.
Just
Could you have more?
yeah, so like most LiDAR samples.
Yeah.
All of those images like
Oh, the question is that did we use surrounding images like 360 degrees views of images? The answer is yes. Yes, we use surrounding images, and we can in nuisance we have 6 cameras for the surrounding cameras.
But each step you have 6 images.
Yeah, correct.
Other questions from the audience? Maybe I can ask you a question. So you are using a lot this BV space, like for the representation. Also, you argued for its utility for building work models, but also for more complex robotic scenarios, like in industrial cases or in home environments, that we can have also some, some objects occupying the same part of the BV space.
Yeah.
Also in driving environments, like you can have like cyclists on bikes, and there can be some intersection. How do you approach this limitation? What do you think about that?
Actually, we didn't do the bird's eye view prediction in robotics because we are managing the image level prediction, and in the driving scenarios we are also doing the video prediction, which are in the image level. So I personally do not believe bird's eye view prediction or image level prediction, which is better, and I can only think about these are very valuable approaches, but in the industry, people are not using now the image level prediction due to its time consuming feature. So, but it is still very valuable to do research to utilize these very strong image generation or video generation techniques these days. And maybe in the future, we can utilize these very strong models, these prediction models in the industry.
Okay, thank you. Maybe a last question, because we're a bit behind time. Any other questions? If not, we can thank Lee again.